Hello, welcome back to the channel. Have you ever wondered what these really weird things are when you look out of the window when sitting on a plane? These things are called winglets. Today I'm gonna tell you what they are and why are they important. Let's go. So, as usual, we are gonna use some sketches to explain what winglets are. Let's start with the definition. So, winglets are a simple extension of the wingtips of the aircraft. And what's their function? They help reduce some parts of the drag of the total airplane. So in other words, they improve the efficiency of the plane. But it's not that simple. So let's look at this sketch. Usually what happens is that the primary purpose of the winglet is to reduce the drag called induced drag, which is caused by the wingtip vortices. That means that when an aircraft wing generates lifts like this, the high pressure air from the wing bottom part flows around the wingtip and creates this kind of vortices. And the drag increases due to these vortices generations. And as a consequence, of course, the efficiency of the plane goes down. Instead, if we use winglets, so this kind of weird small wing, vertical compared to the main wing, we help the efficiency goes up again because we reduce the strength of these vortices right here. In other words, we improve the lift to drag ratio or the efficiency itself. And that means that we can fly longer, or we can fly with a better fuel efficiency, or we can pay less for our tickets, whatever you want to see it. If we want to look at the math part of the wingtip, we have the induced drag, which is defined like this. We have the lift divided by pi, E, which is the Oswald coefficient, B, which is the wingspan, density, and velocity. This value is basically a number that represents how geometrically efficient is the wing itself. So for example, do you remember the Spitfire? The Spitfire has an Oswald coefficient really close to 1, because with this kind of shape of the wing, they were able to create a lift distribution almost elliptical over the wing surface. That means that the strength of the vortices was really low. So in other words, if we want to reduce this type of drag, we have to find a way to reduce the strength of these vortices. And if you're a designer, if you work on the Oswald coefficient, the higher the coefficient, the lower is gonna be this part of the drag. So let's see what kind of types of winglets we have. We can have the Whitcomb, which is like a double winglet. Move on, we have the tip fans, something like this. We have the canted wingtip. This is the kind of winglet that you nowadays see in any kind of planes. And we have the ragged winglet as well. Moving on, if we want to understand how the winglets works, we have to look at their geometric parameters. And why? Because the performances of the winglet itself is heavily influenced by its geometry. So let's start with some kind of geometric things that define the winglet itself. So the most famous one is how tall is the winglet? Which angle does the winglet have compared to the main winglet? The main wing, sorry. So the angle between the main wing and the winglet is called the cant angle. Moving on, we have the tip chord and the root chord. So we have the taper ratio between root and the tip. and also the sweep angle. So that means how backward or forward tilt of the winglet itself. And we also have the angle of attack, or toe angle, whatever you want to call it. And that is the angle of attack of the winglet itself. So if you're a designer and if you want to create the perfect winglet, you can work with all of these different geometric aspects, moving from the altitude, the angle, the sweep angle, the taper ratio, and the angle of attack of the winglet itself. So if you wanna create the perfect winglet and the most efficient one, you've got to work with these geometric features. But if winglets are this beneficial, why don't all aircraft have winglets? So we have some reasons why. Let's start with a design trade-off. For example, if we take an older aircraft, maybe that kind of old plane cannot support the structure of the winglet itself without significant retrofitting. So the cost of putting a winglet inside of an older plane cannot guarantee the performances that we want to obtain. Another parameter, of course, is the cost. Don't forget about this. Winglet increase the manufacturing and maintenance costs. So for example, for shorter flights, the fuel saving may not justify the expenses. Then we have the kind of mission. So if we have planes flying at low speeds or on short routes, for example, regional turboprops, in this case, winglets cannot give you that kind of edge, that kind of advantage in terms of fuel efficiency or aerodynamic efficiency, whatever you want to call it. So depending on the kind of flight and mission you have, winglet can or cannot be the option for you. Moving on, we have the wingspan limitation. So for example, aircraft operating at airports with tight gate spacing may need to limit their wingspan, and longer wings with winglets might exceed these constraints. Last but not least, we have a much higher weight because, of course, winglets had weight and potentially offsetting the drag reduction benefits. And we also have to take into the account the different structural loads over the wing. So additional forces on the wingtip require reinforced wing structures, which can increase design complexity and, of course, again, the costs. So we've seen all the geometric features of the winglet and why don't all aircraft have winglets. I hope you find this video interesting and let me know if you have any question in the comments. See ya!